The sigma notation, the sum of n terms a1, a2, a3, all the way to an is written as this here. So capital sigma is the summation notation. So if you see the index I equal to 1, that's your starting point, all the way to n, which is the ending point. And you have your index somewhere, ai. So this is equal to the first term plus the second term plus the third term, all the way until you get to the final nth term. So you may write down what this means, where I is the index of the summation ai is the ith term of the sum and the upper and lower bounds are n and 1, respectively. All right, so first example. So if you have the sum, well, let's say k equals to 3 to 5. And they give you the formula. The first part is always kind of like your formula. K over k plus 2. So you start at this point 3, and you go all the way until the end point 5. So this would be 3 over 3 plus 2 plus 4 over 4 plus 2 plus 5 over 5 plus 2. So basically, that's all you're going to do. Of course, you would add these up and figure it out, but I want you to see what this means. You should have seen it in college algebra, but maybe not. You can also go backwards. So on the next example, let's try to see a pattern and change it into this notation. So use the sigma notation to write the sum 3 over 1 plus 2 plus 3 over 2 plus 2 plus 3 over 3 plus 2 all the way until 3 over 11 plus 2. And that's where it stops. So you kind of see what's fixed and what's not, what's the beginning and what's the ending, right? Obviously, the 3 stay the same, so the form is going to have a 3 in it. We'll use k, I guess. The one that's cycling through is this 1, 2, 3, all the way till 11. So this is k plus 2. The 2 is fixed. So we start at 1 and we go all the way until 11. All right. So let me give you some summation formulas. number 1. If you sum from I to n, I would become just the last value times that same value plus 1 over 2. Now, if you start at 2, 1 to n, I squared is equal to n times n plus 1 times n plus, oops, actually, 2n plus 1. If you have the same I to n, of I cubed, you get this formula, n squared times n plus 1 squared over 4. So those are the 3 main ones you're going to need. 4, actually. I forgot one. If you're doing a constant from I equals 1 to n, let's say the constant is c, then this would equal c times n, where c is a real number. All right. So let's do the next example using these formulas. So basically, you're going to try to figure out when you can apply these and simplify the question. You guys okay so far? All right. So evaluate the sum I equals 1 to n of I plus 1 over n squared for n equal to 100, 1,000, 10,000. So 1 over n squared times this sum right here. I plus 1. So what you can do is apply this sum to each piece. We're going to ignore this 1 over n squared. So apply the sum to the I and to the 1. And then remember that the formulas above say that this will become, what was it? N times n plus 1 over 2. So this n squared is still there. This becomes n times n plus 1 over 2 plus this becomes n times that 1. Okay. So then add these together. This would be n times n plus 1 plus 2n over 2. So then just plug these numbers in and you'll be good. Because we use the formulas, we no longer have any sums. So we don't actually have to count all the way up until 10,000, right? So n equal to, you simply plug in, well, actually we could simplify this a little more, right? You could pull out an n from the top and have n plus 1 plus 2n over 2. So these will cancel. These will combine, so you're gonna have, oops. No, that's fine. That's good. This should be a 2 though. Yeah. So you'll get 1 over n times n plus 3 over 2. So let n equal 100. This will be 1 over 100 times 100 plus 3 over 2. Simplify this and you'll get what? 103 over 200. And then do the same thing for 1,000. That'd be 1 over 1,000 times 1,000 plus 3 over 2 equals 1,003 over 2,000. No, just do 10,000, the same thing. Anyway, the point is using the formulas will save you time. And it's basically a shortcut. Okay. Any questions on how we use the formulas? Here, see how we use the formula for I, right? This became using formula 1 and 4. Okay, so first, a couple of questions, just plug in the numbers or use your formula for number 2. Number 3, you use your, look at the pattern and find the formula for it. Same thing for 4. Here you can use your formula. This would be equal to 7n, where n is 7. So 7 times 7 is 49. Here, use the formula again. So you're going to use this one here. N times n plus 1 over 2. Just let n be 24, and you'll be good. That makes sense? So the entire section, all you're doing is applying the formula. So right here, you could go all the way up to 5 since it's small, or you can apply the formula to each I once you expand it. This one's general, kind of like this, like the one we just did. You plug in the 10, etc. after you find each piece, after you find the generalized form. Here you do the same, find the generalized form first using the formulas, and then you take the limit. And that's pretty much it. Any questions on 5.2? Let's move on to the last section, if you have no questions. 5.4 is the fundamental theorem of calculus. So if a function f is continuous on the closed interval a comma b, and f, lowercase f, is, oh, hold up. This is capital F, lowercase f. Capital F is an antiderivative of lowercase f on AB. Then following is true. So this is a definite integral, also the first part of the fundamental theorem. So if you integrate from a to b of f of x dx, you will get the antiderivative at the b minus the antiderivative at the a. So basically integrate and then do the new function at b minus the new function at a. And that's all you got to do. So evaluate the definite integral. The integral of from 0 to 4 of 3x minus 1 squared dx. So what I recommend is first multiply that out and then find the antiderivative. So 3x minus 1 squared, it's going to be 9x squared minus 6x plus 1 dx. So integrate each term one at a time. So you're going to get 9x 2 plus 1, right? Over 2 plus 1 minus 6x 1 plus 1 over 1 plus 1 plus x. And then you're going to evaluate from 0 to 4. Okay. So this will become 9x cubed over 3 plus minus 6x squared over 2 plus x from 0 to 4. So this will be 9 times 4. Actually, you can reduce this. Let's reduce it first. Before we apply the fundamental theorem, reduce your function. This would be 3x cubed minus 3x squared plus x. So that'll be 3 times 4 cubed minus 3 times 4 squared plus 4 minus the whole function. I recommend putting a bracket here so you don't mess it up. 3 at 0 minus 3 at 0 squared plus 0. This whole thing is 0, so it doesn't really matter in this case, but it's safer to put that minus in them brackets. So multiply this out, that'll be what? Bunch of garbage. 192 minus 48 plus 4, which is 148. So that is the definite integral from 0 to 4, which represents the area underneath that graph, technically. Any questions on the antiderivative step or the evaluation step. Okay. Cool. All right then. Let's do another one. Let's do a couple of these. Let's do an easier one just in case that was weird. 0 to 3 of x plus 2 dx. So I'm integrating with respect to x. So you're going to get x2 over 2 plus 2x, and then evaluate from 0 to 3. So once you've done the antiderivative, you no longer write the integral symbol. So this will be 3 squared over 2 plus 2 times 3 minus 0 squared over 2 plus 2 times 0. This happens to be 0 again. Cool. This will be 9 halves plus 6, which is 9 plus 12 over 2. Will that be 21, right? Yeah. Okay. Now let's do one that has an actual area. I guess we should do it on the next page. Any question on example 2? You see all it is the antiderivative, and then you evaluate the bounds to find the find this number. Right. So that number represents area. It can represent area. It can also represent all kinds of things, but for now, we're going to focus on area. Calculus 2 is going to go in depth into what other things this can do. Find the area of the region bounded by the graphs of the following equations. So 2y equals 2x squared plus x plus 2. The vertical line x equal to 0, vertical line x equal to 3, horizontal line like y equals to 0. So basically, if you graph this, right, let's say that 3 is over here. You have this vertical line going this way. And then you have the vertical line over here for 0, which is the y-axis, right? Then you have your parabola kind of doing this number, something like that. A little too straight. So we're going to find the area of this. Just so you can see it better, I'm going to graph it on Desmos because that looks pretty lame. There it is. Okay, so we have the parabola y equal to 2 x squared plus x plus 2. Then you have the vertical line x equal to 0, x equal to 3. So the area that we're finding is in here. So basically this here. So that's what we're looking for. The area from 0 to 3 all the way up to here. That's what I was kind of trying to draw. Something like this, right? So when you create your integral, you do the integral from, since we're doing dx, you're going to be going this way. So picture little rectangles with thickness dx going from left to right. So if it's dx, we're going to go from left to right. So from 0 to 3, 2x squared plus x plus 2. So it's always going to be, well, I should show you one more step here. It's always going to be the top function, which is this one, the parabola, minus the bottom function, which is the horizontal line y equals 0. So it doesn't actually make a difference, the 0. So you integrate this term by term, you get 2x cubed over 3 plus x squared over 2 plus 2x from 0 to 3, from this 0 to 3. So this will tell me the area underneath. So plug in the 3. Subtract the function at 0, which in this case, again, zeroes out. So all we got to figure out is this now. So that'll be 2. Yeah, you know what? Let's just punch it into the calculator. D7 over 2. So the area underneath is this. So that's one of the applications. Sorry, I lost my train of thought. So one of the applications of integrals or antiderivatives is finding area underneath curves. And this is the area under here, between these lines and under the graph. Any questions on this example? So that's all you're going to do here. You're going to integrate the function and then evaluate the bounds. Integrate these two terms, evaluate the bounds. Well, this one you'd have to multiply out, but and some of them will be a little harder, but it's the same thing over and over again. Okay, the last one is going to be find the area underneath the graph. So you can integrate cosine, but remember it's going to be 0 to pi 6, wherever the function stops, wherever the shaded region stops. 12 is the one we just did, very similar. So you're going to graph it yourself and then figure out, okay, where am I integrating from? Most likely is going to be 0 to 2, but you should graph it to check. And then you'll do what we just finished doing. This is the same thing. Any question on those concepts? Can you find the antiderivative and plug in the upper and lower bound? Can you find the area underneath a graph? Does that make sense? All right. Well, that's it. That's the last section for Calculus 1. We finished. We made it.